Good morning, sir. Myself, Neeraj Kumar from CSCD section. My topic is about the particle in one-dimensional potential well, eigen wave functions. On moving on to the first slide. First of all, introduction to the quantum mechanics. The quantum mechanics describes the behavior of the particles at the atomic and subatomic levels. So it has fundamentally differs from the classical mechanics in its treatment of particles as wave functions. In understanding the quantum system, it is crucial for explaining phenomena such as atomic structure and chemical reactions. And we'll learn about the concept of the potential well. A potential well is a region in space where a particle experiences a lower potential energy compared to its surroundings. In one dimensional, this can be visualized as an infinitely deep or finite well. The shape of the potential well influences the allowed energy levels of the particle confined within it. So next we'll learn about the types of the potential wells. There are mainly two primary potential wells. The first one is infinite and the second is finite potential well. An infinite potential well has infinitely high walls that confine the particle completely. And then the second one, a finite potential well, allows for some probability of the particle existing outside the well, leading to different eigenstates. So let's see what is its equation. Schrodinger equations. The Schrodinger equation is the fundamental equation of a quantum mechanics governing wave functions. For a particle in a potential well, it describes how the wave function evolves over time. Solving the Schrodinger equation provides the energy levels and eigenstates of the system. And then the boundary conditions. The boundary conditions are essential in solving the Schrodinger equations for a potential well. For an infinite potential well, the wave functions must be zero at the boundaries. So for the infinite, the wave functions must be zero. And these conditions lead to the quantization of the energy levels and specific eigenfunctions. And then about the eigenfunctions and the eigenvalues. Eigenfunctions are specific wave functions that are solutions to the Schrodinger equation under defined conditions. Each eigenfunction corresponds to an eigenvalue which represents the energy of the state. The quantization of these energy levels arises from the boundary conditions which are imposed on the system. So in the beside we can see the equations. And then the infinite potential well energy levels. For an infinite potential well, the energy levels are quantized and given by here is the equation of it, and here n is a positive integer which representing the quantum number, and h bar is the reduced Planck's constant, and m bar is the mass of the particle, and L is the width of the well. As n increases, the energy levels become increasing spaced apart. And then the energy levels of the finite potential well. In a finite potential well, the energy levels are also quantized but different from those of the infinite well. Some energy levels can be below the potential height, allowing for classically forbidden reasons. The energies are determined mathematically through transitional equations derived from the Schrodinger equation. And then the wave functions of the finite potential well. The wave functions for a finite potential well consist of decaying exponential outside the well. Inside the well, they are similar to those of an infinite potential well, but with different boundary conditions. The probability of finding the particle outside the well is non-zero for the certain energy levels. And then let us see about the quantum tunneling. It is a concept or a phenomena where particles can pass through barriers even if they don't have enough energy classically. This occurs in finite potential wells where wave functions extend into classically forbidden regions. So the tunneling has significant implications in various fields. It includes the nuclear fusion and the semiconductor physics. And then let us see some applications of the potential wells where it can be used. Potential wells are foundational in understanding atomic and molecular structures. So uh, in the atomic and molecular structures, these potential will be applied. And then they also plays a crucial role in technologies such as quantum dots and semiconductor devices. The principles of the potential wells are also applied in designing quantum wells for the lasers and photonic devices. And then visualization of the wave functions. The graphical representation of a wave functions helps in visualizing the probability distribution of the particles. Plots illustrate the nodes and the antinodes of the wave functions within the potential well. So in the beside picture you can see the graph. It is a graphical representation. So the nodes representation illustrate the plots and the antinodes of the wave functions within the potential well. So in understanding these visualizations, in grasping the physical implications of the quantum mechanics. So, some of the summary key points. The particle in a one dimensional potential well illustrates fundamental quantum mechanic principles, and then the key concepts include quantization of the energy levels, wave functions, and tunneling phenomena. Mastery of these topics is essential for advanced studies in quantum physics and related fields. Uh, that's it. Thank you.